Hey guys, my name is Geleting Sefoloko. We are analytical chemistry students and we will be talking about the sulfate removal in industrial effluents using electrocoagulation as an absorbent.
Greetings to you all. I am Sivezim.
Hi everyone, my name is Umpile Slad.
Greetings everyone, my name is Vanille Siyoko.
Greetings everyone, my name is Tolan Sibeng.
Our research is about sulfate removal in industrial effluent using electrocoagulation sludge as an adsorbent. The problem is the excessive concentration of sulfate that harms the infrastructure of wastewater treatment plants. And in this research, we present the application of electrocoagulation sludge as an adsorbent to remove sulfate from the industrial effluents before they are released back to the environment. Iron and aluminium cation as well as the cationic complexes are present in the sludge, causing the sulfate precipitation in water. The iron sheet is used as a sacrificial electrode in the electrocoagulation to produce the sludge. Recycling in biological waste is critical for preserving our ecology. This approach helps to address the environmental issues such as the volume of waste sent to the landfills, while also creating opportunities for economic gains through the preservation of natural resources. These resources, which are mentioned as timber, water, mineral, as well as improve their security through the use of domestic resources. The recovery of enhanced commodities from the garbage is unquestionable and one of the most important phases of waste management. Electrocoagulation has found to be the most effective method for removing sulfate by producing precipitant, adsorbent, and coagulants from the zinc, iron, and aluminium using the sacrificial electrode. Water composition, pH, and redox potential all affect the removal procedure in the electrocoagulation.
I'll be talking about the apparatus. The apparatus consists of the electrocoagulated cell, which is the reactor, anodes, and the cathodes, which are both inert, power supply, control panel, and pumps. For the apparatus to work at optimum condition, the pH has to be at 6, contact time 20, applied voltage at 15 voltage. Initial concentration of the reactant should be at 50 parts per million.
Methodology: for preparation of the sludge or adsorbent from a corrugated iron using electrocoagulation system. First, you have to collect the wastewater from the battery industry. Then the percentage of the composition of battery wastewater is removed by the electrocoagulation process and discharge limit. Dry the sludge or adsorbent obtained after electrocoagulation for roughly 8 hours at about 105 degrees Celsius. Then crush the absorbent and store it in a desiccator. The second part is batch adsorption experiment. It is performed in a 600 ml aluminium flask filled with 500 ml of water containing the preferred sulfate concentration. Shake the flask containing varying concentrations of adsorbent in a shaker for 120 minutes. Then find the effect of pH on sulfate removal using absorbent doses of 400 mg for sulfate concentrations of 100 mg per liter. While keeping the absorbent dose constant at 400 g per 500 ml, perform the adsorption isotherm test with varying sulfate concentrations ranging from 100 to 250 mg per liter. Then after, use the concentrations in solutions before and after adsorption to compute the quantity of sulfate absorbed. That part is for adsorption isotherms and kinetic studies. Find the effect of contact time on sulfate removal, then determine the kinetic parameters using pseudo first order and pseudo second order models. Lastly, for preparation of sludge or adsorbent for reusability, the sludge that are used as an absorbent is regenerated using an acid or a base treatment. After each adsorption cycle, the absorbent is washed with deionized water 5 times and re-dried in an oven set at 80 degrees Celsius for the adsorption of sulfate in the next cycle.
Solution overview. When iron and aluminium electrodes mix with water, they create a useful sludge. This sludge then acts like a sponge, absorbing sulfates from industrial effluent. The sludge positive charges grab onto sulfate pollutants, allowing complete removal. The sludge's sponge-like texture will then make it super effective to soak up sulfates. Then maintain optimal pH condition to allow the sludge to work at its best on removing sulfates and minimize interference. This process ensures that sulfates are locked for good, preventing them from leaking back into the environment. In other words, it is eliminating risk of repollution.
There are multiple factors in the process that contribute to a high magnitude of separation of sulfates and contaminants from water. Our first slide shows the characterization of the electrocoagulating sludge. As seen on our spectrum, there is a formation of iron oxides. The iron oxides assist greatly in catalytic activity and separation. Another factor that has had an impact is the surface area of our sludge. As seen on table 2, a larger surface area provides numerous sites for adsorption. Graph A and B display the optimal conditions for separation. The two graphs highlight that sulfate removal is most effective at lower pH levels. The efficiency tends to decrease as the pH increases. Additionally, moderate concentrations appear to optimize the removal process. Table 1 summarizes the factors in numeric data. We see that a staggering 99% separation of sulfates from industrial effluent was achieved, and a high separation of 95% was obtained from the synthetic effluent. The absorbent can be used through 4 cycles. It is cleaned with deionized water and dried for a period of 4 hours. This demonstrates the recyclability of the absorbent, which minimizes wastewater treatment costs.
In conclusion, EC sludge produced by the electrocoagulation process was successfully used to remove more than 95% of the sulfate in industrial effluent and synthetic sample at low pH. Therefore, the water is returned to the environment for people, animals, and plants.
Acknowledgements. We are grateful for the input and expertise of several individuals who helped shape this research. A thank you to Ms. S. Yamba and the team in making this presentation possible. We are honored to share your findings with the audience.